Okay, the last example for question number 2 looks at another exponential equation, and it's very similar to the previous question that we looked at. Again, I have one term on the left-hand side and one term on the right-hand side. And again, I can't change the base of 7 easily to make it a base of 4. And so I'll find the logarithm of both sides. And then I'll apply the power law of logarithms so that I can bring down the exponents. So I have 2x plus 1 times the log of 7 equals x minus 2 times the log of 4. And you'll notice again that because I have a variable term on the left-hand side and a variable term on the right-hand side, I actually need to apply the distributive property so that I can eventually bring all the variable terms to one side and all the number terms only to the other side. So I'll do the distributive property on the left-hand side to get 2x times the log of 7 plus the log of 7. And that'll equal x times the log of 4 minus 2 times the log of 4. Okay, and then I'm going to bring all the variable terms to one side and the number terms to the other side. And again, it really doesn't matter which side you take them to. So this time I'll move the logarithm term to the left-hand side and the number term to the right-hand side. And so I get 2x times the log of 7 minus x times the log of 4. And that'll equal negative 2 log of 4 minus the log of 7. Okay, so now the left-hand side, the first term and the second term both have a common factor of x. Again, I can't factor out a log because that logarithm needs to be applied to something, and the first one's applied to a number 7 and the other one's applied to a value of 4. So I can only factor out an x, and I get 2 log of 7 minus the log of 4 equals negative 2 log of 4 minus the log of 7. And then I can divide both sides by the brackets on the left-hand side to isolate x. And so I'm left with x is equal to negative 2 times the log of 4 minus the log of 7 divided by 2 times the log of 7 minus the log of 4. Okay, and there you have it. That's the exact value. Now you can find the approximate value by using your calculator, but in this case, because the question asks us for an exact form, we'll leave it at that step. Okay? And there you go. Okay, so those are some easier examples of solving exponential equations using logarithms. But what happens is, oftentimes you may have an equation where one side of the equation has more than one exponential term. So here's an example here where the left-hand side has 2 different terms and the right-hand side has one single term. Now, because there's more than one term on the left side of the equation, you cannot take the logarithm of both sides. You can only find the logarithm of both sides if you have a single term on the left side and a single term on the right-hand side. So, what do we do? Okay, we need to use another technique, and so the other techniques that we can use to solve exponential equations are factoring and the quadratic formula. Now you might be thinking, how are we using the quadratic formula when we don't even have a quadratic equation? Well, what happens is the exponent parts may create an exponential equation if you only focus on the exponent parts, and so as a result we may be able to use the quadratic formula. Okay, factoring is another option. We looked at some factoring in the warm-up, and you may see some factoring in the examples that we're going to see shortly as well. Okay, to sort of elaborate with the factoring, the example that I have here, which is 2 times 2 to the exponent x plus 2 minus 2 to the exponent x equals 24. This example here you can actually solve by factoring, and we're going to do this one in a few minutes. Okay. Before we do that, there's a concept called extraneous roots that we're going to look at. And what an extraneous root looks at are solutions that you cannot actually have. So there's solutions that you get as a result, but there's solutions that actually don't make sense with the original problem. Okay? So it's sort of like when you had questions where you were solving for a dimension in grade 10 or in grade 11, and you might have had examples where you had a negative dimension, and well, that doesn't make sense with the original problem, so you ignored those solutions. So extraneous roots do exist as well for exponential functions, and essentially these extraneous roots end up being uh, negative values for your solution, which you can't have when you're looking at the power of a particular base, or an exponent on a particular base. So extraneous roots usually look at solutions that don't make sense. Okay?